So how do we graph all of these fun things without Desmos? Well, the answer is really the same way that we have been. It's just understanding how to take what you guys have learned. I'm talking about things you've learned about asymptotes, about holes, and other ideas, and take them and understand how to draw a pretty picture. Okay. The other thing that you want to understand is that I'm not going to be giving you the hardest problem ever. Sometimes people's mind goes, oh my gosh, how am I going to do this problem? And you kind of think of like the hardest problem we ever did. I'm not going to give you one like that, but I am going to ask you to be able to navigate the essentials. This is not something that we do a lot of, but we have done a little bit this year, right? I've made you graph sine and cosine without a calculator. I don't want to say that you've forgotten, but maybe, you'd have to refresh on it. We've also graphed some other things without a calculator. We've graphed polynomials. Now, again, I hope you haven't forgotten completely about behaviors of polynomials. We'll review it a little bit for the final. But that's kind of annoying. That thing keeps flashing. I didn't realize that flashed. So today, though, we're going to graph rationals without, again, the help of Desmos or a calculator. Okay, now I will give you some pointers, but I have found that for this lesson and this topic, it's kind of helpful to realize these things through, obviously, an example. And we're going to kind of keep it simple today. I actually just have two examples, and I'm going to give you a little exit question, which is supposed to try to force you in the confines of the classroom to try to do one of these. All right, so you don't have to get out Desmos. I know that's a lot of work. We're just going to use the old brain. Negative of 2x minus 4 over x squared minus 4. So again, the good news, everything you guys have learned about asymptotes, and that's actually where we're going to start, and holes, I guess, forgive me, that's actually where we're going to start, is still true. So really the hole, or I should say the potential hole in the graph, should be the first order of business. And really, maybe even before we start making this list, your first order of business is just kind of look at this equation and say, I feel like there's some factoring I can do. I feel like there's some basic math that I've seen before. And I always say that if you see that, then you should do it. This darn negative sign right here, I'm having trouble with. I don't want to forget about it. So there is a negative sign, but we're going to factor the denominator. It's kind of one of those things that, yeah, if you see factoring, you should do it because, well, it might shed a little light on this problem. So I'm going to factor the denominator. You realize that the numerator can also be part of this factoring game. You can actually just factor out a 2. Now, I'm not sure if we've had a problem like that much in the last week or so, but I know you guys know how to factor out a 2, so sure, let's do that. Okay, how are we doing so far? We're just kind of recognizing that we can factor. What I hope, though, that you really are recognizing is that we have some special stuff going on. So that x minus 2 over x minus 2, that should catch your attention for sure and realize that that's going to be a hole. Now, when you say there's a hole, you say the x value. Now, the x value would be the bad number. So yes, x equals 2. X equals 2 is a bad number, so the hole is at 2. But I hope you haven't forgotten that we actually want to give the y value. What we really want to do is give the actual point value for this hole. This is something that some of you, I know you need a little more practice with, so that's why I'm doing it again. I'm going to cross out the common factor temporarily. When I cross it out temporarily, I get this temporary equation. Now notice, once again, I'm not going to forget the negative sign. As you may have noticed, I actually put the negative sign in the numerator. You're allowed to do that. You got to put the negative sign somewhere, so we're going to put it in the numerator. That's my temporary equation, and it's able to accept x equals 2. Like, I can now plug in 2 safely. Safely meaning I'm not going to get a 0 in the denominator. I actually end up getting 2 over negative 2, negative 2 over 4. But I would hope that you would change that to be negative 1/2, just because that's obviously what it's equal to. Okay, what just happened there? We found the y value for the whole. And that is better, that is more specific than just giving the x value. Okay. All right, now I don't want to say I'm glad we're done with that, but we're ready to continue, kind of back to familiar stuff, talking about some asymptotes. Okay. Hey, remember, there's another bad number. It's negative 2. So don't forget the basics. Negative 2 is a bad number. That's going to be a vertical asymptote because there's nothing else it can be. Good.
This one really checked out a few days ago, but vertical asymptote, it's not going to be at where the hole is too, right?
Correct.
It's just the other number of the factor.
That is correct. A hole, you can't have a hole and a vertical asymptote at the same place. And so sometimes kids will say, okay, the hole overrules, right? Right. The hole kind of overrules the asymptote. But I can have an asymptote at a different place, which obviously happened here. There's a test early next week. At that point, you have to know these rules. Are you getting to know them? Horizontal asymptote, degree. Comparison, honestly, it's comparison of the degrees. Notice I went back to the original equation to say degree 1, degree 2. Survey says, that's kind of my way of saying the answer is y equals 0. Little Family Feud plug there. That's always a fun show. Everybody's always happy and clapping and stuff. Okay, do we have to write slant down? You know, there's no slant. The top is smaller than the bottom, so I'm just going to skip that. But let's do the y-intercept and probably the x-intercept. Oh, yeah, back to this. Okay, remember, a y-intercept is if you plug in 0. If you plug in 0, now, you know, back to the good old equation, okay? Back to the good old equation. I don't really need to go back to my factored equation to plug 0 in. And maybe you can just see that it's negative 4 over negative 4, which is really 1. So 0, 1.
Yeah.
Ah, dang it. Very good. You're a little sharper than me here. Seriously, very, very good. I told you I was having trouble remembering that negative, and that would have messed us up. All right, so we actually end up with 3 negatives over here, which is why we end up with a negative 1. And again, thank you. X-intercept, okay? Set the equation equal to 0. Now, when you set the equation equal to 0, the only thing that can equal 0 is the numerator. Okay, that's because the denominator can't equal 0. So I don't want to say cheat, but I can kind of save a little thinking and just say, okay, the numerator is equal to 0. Now, I did it again. The numerator actually has that negative sign. So what I really need to do here is put this negative sign in front of my numerator.
It's kind of a tough question, but when the negative's like out in front of the whole like equation, does it always go to the numerator or does it not matter?
It doesn't matter. But here's what does matter, that you put it to the numerator or the denominator, not both. Can't put it to both, because if I put it to both, then I don't have a negative anymore. And here's kind of what I was catching myself on. It's got to go to the whole numerator. So negative of the whole numerator, the parentheses. Okay, so it doesn't matter, but make sure it goes to the whole thing. Now, are you guys kind of like chewing on solving this thing? You can distribute the negative. That actually would save us a lot of frustration here. Just distribute the negative. It's still equal to 0. X equals 2. But actually, I'll say that x equals 2, more like a question. The reason I'm saying x equals 2 as an x-intercept is because we have something interesting happening with x equals 2. It's already been classified. You see, the whole kind of overrules. So once again, I can't have a whole and an x-intercept. You say, well, why not? Well, technically, if you're going to write down 2, 0, you're describing a point, like a good old point on a graph. And you can't have a point at 2, 0, and then in the other breath, have a whole at 2, -1/2. I can't have two things happening at 2. So guess what the final answer is for the x-intercept? There is none. There is none because there's no other number available. And as we said, you can't have a whole and an x-intercept at the same place. Okay, now I told you that the problems that we do are going to be, I'll say, a little bit more basic. I mean, this one obviously had a lot going on, so we could talk about it together. But still, when we go to graph this, we should say that there's ultimately a couple things to consider. There's a vertical asymptote. There's actually a horizontal asymptote. Kind of back to the basics. Now, there is this hole in the graph. We want to be careful that we mark 2, -1/2 in the correct position. It's just a sketch, so, go 2 and then go down -1/2. And then we also have a Y-intercept. And again, it's just a sketch, but if I'm going to go down -1, I got to go down a little further. Here's the part of the lesson where I hope that you make some connections from prior things that we've done and realize you don't need Desmos to start to draw this, because there's got to be something true about your graph and its interaction with these yellow features. Let me say that again. There's got to be something true about your graph and its interaction with the yellow features. First off, if you have a point and a hole, guess what has to happen with your graph? Okay? It's got to go through them, right? That's what points are. They're points on the graph. So I have to go through the points. What about these asymptotes? What about these asymptotes? Well, you've seen them numerous times, and you should conclude that a graph is going to approach asymptotes. It gets closer and closer. And so I can actually extend my graph down here using the same wisdom, which is that the graph is going to go through the points and it's going to approach the asymptotes. Now, I have that up here as a little pointer. It's just said the other way. But do you agree with that? I say, do you agree with that? But you should agree with that. That's how all the graphs have been. Graphs are going to approach asymptotes and pass through intercepts. That is a great pointer. Now, I know that takes a lot of work. What we just did took a lot of work, although it was pretty easy to draw the graph after we did the work. But there's something missing, and I'm appealing to the fact that you've seen a few of these graphs in the last week. So you should feel like, there should be something else. There should be another branch. There should be some other part that I draw. And the question, honestly, is where? Now, it's either or. So honestly, it's one or the other. The reason it can't be this one is because it wouldn't be a function anymore. If I draw the graph up here, now I'm not passing the vertical line test. So try to kind of keep it simple. It's one or the other. And what I'm going to show you right now is a little analysis about positive and negative numbers. Because think about it, every number here, now I'm talking about the y values, every y value is positive. But here, every y value is negative. So there's a real simple analysis we can do about positive and negative. And it just has to do with evaluating an x value that is on this side of the asymptote. Now, the asymptote's at -2. That's an important number. But now all I need to do is evaluate an x value. Notice I chose x equals -3. I mean, it's like the closest one. And all I have to do is evaluate it to find out if it's positive or negative. Now, when I say evaluate, I want to make sure you guys understand I'm just talking about plugging in. And sometimes a basic little plug-in, input, output, is all that's needed to complete this graph. Now, I'd encourage you to think about this math without your calculator, because you guys can multiply by -3. Oh, guess what I did again? Forgot that negative. Okay, so we can do this. I'm not sure if the teacher can, but we can do this. We can plug in -3 and, multiply, square it. -6 minus 4, that's -10. Now, there's still a negative. I'm going to make sure I don't forget it. So I'm choosing to put the negative up with the numerator. So I get a negative of a -10. And then I'm going to get 9 minus 4. Now, be careful. 9 minus 4. Okay, that's 5. Now, since I'm being careful about the negative that I have forgotten a few times, I see that, I see that I end up with +2. Now, I'll be honest, the most important conclusion here is positive. Positive. That means that there's a point at -3, +2. But it also means that all the other points are going to be positive because of what we know about the shape of this graph. We know that the graph is going to have to approach the asymptotes. And so it kind of like gets itself in that corner. Oh. Boy, if you guys come out of this understanding it, we'll be very fortunate. Although if you're noticing that stuff, that actually is good, but I'm not trying to confuse you.
So when you're plugging in a point,
When I'm plugging in a point,
you just plug in the x value, but then what are you looking for?
I'm looking for the type of output. I'm looking to see if the output was positive or negative. The output's the y. So once I concluded that the output was positive, even though I wrote it backwards,
so if it would be negative, that would be it.
It would have been down here. Let's look at one more. We'll be able to look at it a little more quickly. Hopefully I don't make it confusing for you. I do want you to have an opportunity to try one of these, like an exit ticket. All right, so x plus 2 over x squared minus 9. problem is kind of designed that you could do a little bit of what we did in the other one. I can tell that you're already okay, so again, factoring is a good idea. You just never know. Although I think I know after factoring that there's not a hole in the graph. So I'm honestly going to just kind of bypass that. I'm not going to write down hole. I'm just going to go right to the vertical asymptote. Okay, now make sure you realize that there's vertical asymptotes. I mean, these numbers, namely -3 and 3, they're bad numbers. So, they are something. They're vertical asymptotes. Maybe you just want to simplify it a little bit by saying plus or minus 3. How are we doing so far? Okay, horizontal asymptote. Again, very similar. So we'll have to say y equals 0. If you plug a 0 into the equation, you get 2 over -9. I think we can just kind of see that. 2 over -9. 0, -2/9. Now, the x-intercept is when the numerator is equal to 0. This time we do get a number that has not been classified. So, yeah, I can use -2 as my x-intercept. Shoot.
So when you're doing the intercepts, you'll go back to the original equation?
Yeah, you go back to the original equation. Listen, you could plug into this equation. If you like the factored equation, you could plug in 0. It just it's more places to do it. You're still going to end up with -2/9. Again, it's usually a little harder to do. Okay, as you get your graph ready, it certainly doesn't need to be said that it's got a little bit more going on. I mean, this one was harder to do, mainly because the teacher kept messing up, but this one has more spaces. And I just kind of want to stand before you and say that when you have vertical asymptotes, they divide a graph into spaces or into intervals. So I want you to feel like you kind of have the space to the left of -3. I want you to feel like you have the space that's between the 3's. And then we have the space to the right. Not to mention we have a horizontal asymptote also cutting through the middle. But it's the vertical asymptotes that kind of divide you into spaces. What about our little pointers here? The branches are going to approach asymptotes, pass through the intercepts. Okay, well, I've got a couple intercepts here. I've got a couple that I can pass through. Now, here's the next question. Are you ready? How do I know if it does that? If you've been around here lately, you've seen that. Or how do I know if it doesn't kind of like do this? Well, there's actually a good answer. And it doesn't require plugging numbers in. It just requires realizing something about this one. There's a reason it's not that one. Do you see why? It's interesting that you say that. There could be something about a square that would make this, yes, you're right. If that was a square, that would feel like this is more like a parabola. You're actually right mathematically. Most kids are going to be like, wait a minute, how do you know that? There's an easier way to know, though, so that everybody can kind of feel comfortable here. Well, again, I'll be honest, you don't have to be that fancy. It actually just has something to do with the graph. It has something to do with this right here. Look what you just made. Well, you made another x-intercept. Maybe it's symmetrical, but seriously, you just made another x-intercept. That's the only x-intercept. Okay, so, oh, cool. I don't have to wonder. I can just assume. I hate using the word assume, but there's nothing else it can do. It can't have another x-intercept. Okay, that's a little fancier, but it is true. I'm trying to, of course, tell you the truth. Now, you see what's going on over here? We actually have to investigate, evaluate. And most people are going to pick 4s because, honestly, they're as close as we can get to the asymptote. If you don't like the number 4, then you can pick 5. But I forgot to put this up on the screen, although we said it. And I just want to make sure you guys realize that we're investigating points near the vertical asymptotes. As you can see up on the screen, we're going to investigate points near the vertical asymptote. Okay, now don't rely just on your friend to do this, or the teacher, because, well, you can already see the teacher's not done it correctly all day, but be able to plug in -4. Be able to make a conclusion. The conclusion is -2 over 16 minus 9, which is actually -2 over 7. Which is negative. Okay, to be honest with you, the conclusion is really that it came out negative. Now be careful, the denominator is 16 minus 9, that's +7. But -2 over +7 is negative. So guess what? When I plugged in -4, I got a negative number. Okay, that means that your graph is going to stay down here. It's going to be negative. Trust it. It's true, or else I wouldn't be giving you this idea. And then we can plug in 4. And if you can do this a little faster, awesome. If you already came up with a conclusion, great. But you're basically going to do 4 plus 2, and then 4 squared. 4 squared minus 9. So now we get 6 over 7. But again, the real conclusion is that it's positive. And if it's positive, when I plug in 4 and I get a positive number, that means there's a point up there that's positive. Of course, it also means my graph. Pretty fancy graph, especially without Desmos. That's about as fancy as we'll get. Now, kind of for your own good, if I can say it that way, I want you guys to try one of these in the time that remains. When you do your homework, you kind of have to be disciplined yourself, like without using Desmos. But at least when we're in here together, we can sort of all police each other, and without using Desmos, can you graph this. I tried to make up one that's pretty fair and reasonable. It might even be the easiest one today. See if you can come up with a nice graph. You can talk about it with your neighbor, but I encourage you to try to do as much of it on your own and maybe not talk until maybe near the end.